All right, we're going to get started. Welcome, Joop, Noorman, for what's new in ir3.
Thank you. Can everybody hear me like this? Great. So my name is Joop. I'm a member of the compilers team at Igalia. And about a year and a half ago, I got the opportunity to work with some of my colleagues in the graphics team on a compiler backend for GPUs. I had never worked with GPUs before or with anything graphics related, so this was a great opportunity for me to learn something new, which I did over the last year and a half. And today I wanted to talk a bit about what ir3 is, some of the new things we've added over the last year and a half, and if time permits, also a bit about the tooling that we use that I have found very useful. So let's start with the basics. What is ir3? Most people probably know that ir3 is the compiler backend for Qualcomm Adreno GPUs in Mesa, which means it's used by both the Gallium driver Freedreno and the Turnip and the Vulkan driver Turnip. We support a wide range of Adreno generations, starting from the A300 generation up until the current generation A700 that we're mostly focused on. As for the name, as far as I know, ir3 just means intermediate representation 3. Thanks. Where the 3 refers to the first generation that we support, A300. So before that we had ir2, and from the A200 series to the A300 series, there was a big change in the ISA, and a new backend was needed. And since then, this backend has been used for all the later generations as well. Let's talk a bit about the Adreno ISA. Like most contemporary GPUs, it uses a SIMT architecture, where we can either use 64 or 128 threads per wave. From the viewpoint of one single thread, it's a scalar ISA. We don't have any vector operations, save from a few memory loads and stores that can use vector registers. So load store ISA, most ALU operations cannot directly address memory. We need to have separate memory loads and stores for that. There's native support for both 16 and 32 bits, integer and floating point operations. And we can do kind of arbitrary branching. We need to help the hardware a bit by marking convergence points in the instruction stream. But aside from that, we can branch arbitrarily. We also have a limited form of predication, which is kind of a way to explicitly modify the execution mask of the wave. Adreno supports a bunch of different types of execution units. The main one is the vector ALU, where a certain operation is executed for all the threads in a wave. One thing that was very interesting for me, or very unknown, so to say, is that this thing has a fixed latency. It takes a fixed number of cycles before a result becomes valid after dispatching the instruction, and this has to be managed by the compiler. So the hardware, if you want to read the result of a vector operation, the compiler has to make sure that enough cycles have passed, and this might include inserting NOPs if necessary. There's a special function unit for more complex operations like the square root. This kind of executes in parallel to the vector ALU. And this one has a variable latency that needs to be managed by the compiler, again, by introducing a short sync flags whenever we want to read the result of an operation. Then the scalar ALU, so again, for me, a very interesting concept, but here, this is used for uniform operations. So operations where the same value is calculated over all the threads in a wave can use the scalar ALU, which means it's mostly used in the preamble. But we can actually use it wherever in the main shader as well, as long as the values are uniform across a wave. Here there's no latency, so whenever the result of a scalar ALU operation is used by another scalar ALU operation, we don't have to insert any synchronization code. If we want to use this result in the vector ALU, we do have to do it again with synchronization flags. Then there's a texture processor and load store units that also execute kind of in parallel. I'm not going to talk too much about it, aside from saying that, again, this has a variable latency that needs to be managed by the compiler, this time with a different synchronization flag. We also have a bunch of different register classes, the main one being the vector GPRs. We have quite a lot of them. In the ISA, we can encode 48 VEC4 registers. But the total amount of GPRs is shared among all the waves, which means that the more GPRs you use, the less waves you can launch in parallel. So we really try to reduce the register pressure as much as possible. One interesting aspect here is that from A600 onwards, the 16-bit registers that we support, they overlap with the bottom half of the 32-bit registers, which introduces a bunch of interesting challenges in the compiler. It also gives some opportunities for interesting optimizations. Then there are the shared or the uniform GPRs, kind of what I think what are huge GPRs on AMD. These are used mainly by the scalar ALU to store uniform values. They're also used for the implementation of some subgroup operations, as they allow to broadcast values from one thread to other threads in a wave. There's a very limited set of registers called predicate registers, which are only used for branching. They can only be written by a limited set of instructions, for example, compares, and they can really only be used for branching. So you cannot read them, you cannot copy them, or do anything else with them. And then one last one I wanted to discuss are something called constant registers. This is a pretty interesting register class as it's backed by uniform memory. But they are addressable like any other register by most instructions. So most instructions can address at least one constant register, but it's actually a kind of a memory operation without the latency that you would normally get from a memory operation. It's up to the driver to decide what to do with this constant register space, and we, for example, use it to lower UBOs, push constants, or driver params to these registers. I want to give a quick overview of the compilation flow. There's nothing too exciting going on here, so I'll go quick. So we start out with NIR coming out of either Gallium for Freedreno or out of Turnip for Vulkan. We lower this NIR all the way up to a point where it's very similar to ir3, so it looks like almost legal ir3, which means that the next step, the instruction selection, is mostly one-to-one mapping. There are, of course, some exceptions. Some instructions are a bit more difficult to map, but many of them are just a simple mapping from NIR to ir3. We create a control flow graph as well. I'm not going to talk too much about this. Then we have a bunch of optimizations, and we do most of the optimizations in NIR, but a few of them are very ir3 specific. So, for example, coming out of NIR, all the immediate values that we have are translated to move instructions, because move instructions can encode any valid 32-bit immediate, but many ALU instructions can also encode an immediate, limited immediate value. And so there's a copy propagation step that really tries to propagate all these values directly into ALU instructions. Then there is our first scheduling step. So before register allocation, we have a scheduler that tries to reduce register pressure as much as possible to make sure we can launch as many waves in parallel as possible. And one side note, by the way, up to this point, we're still in SSA form. So we consume NIR in SSA. All the way up to the beginning of the register allocator, everything is in SSA. And only during register allocation, we actually go out of SSA. I won't talk about the register allocator because Connor, who wrote this, gave a talk about this, I think, about 2 years ago, or 3 years ago, so we can listen to that. After the register allocator, we have a second scheduler, and this time it's a scheduler that tries to reduce latency. So because in the next step, our last compilation step, we have to legalize everything. So any delays that might be necessary to be able to read correct values need to be inserted in NOPs, for example. And so this the second scheduling step tries to reduce the amount of NOPs or reduce the amount of stalls introduced by synchronization flags as much as possible. And then after this legalization, the last step is the assembly to binary, and we use ISA spec for this. So that's a bit of an overview of what ir3 is and how it works from a high level. Let's talk a bit about what is new. And I'm going to talk about the things that I've seen happening in the last year and a half. That doesn't mean that it's all done by me. This has been a group effort from multiple people working on ir3. First, a bit of a status. If I'm correct, I think we actually implement most major hardware features all the way up to the A700 series. I'm aware of a few instructions, for example, that we're not using yet, but I'm not aware of any main features. Of course, this is a reverse engineered ISA, so things might still pop up that we don't know about, but for now, most of the main features are implemented. I've split what happened in the last year and a half in two separate groups. Older features that were already present in the A600 series, and then newer features that were added in the A700 features series. For the older features, one of the big ones that Connor worked on is support for the scalar LLU. So we were already supporting in a limited form these scalar registers, but we're kind of emitting them in very specific situations manually. Connor added full support for the scalar LLU to use it in the preamble or wherever we have uniform values. Related to this is support for early preamble. So it turns out that this scalar LLU is not only embedded in the shader processors, but there's also this component called the high-level sequencer, which is kind of responsible for dispatching waves and scheduling waves, and it also has a copy of the scalar LLU embedded, which means that we can launch preambles that only use the scalar LLU can be launched earlier before any waves get dispatched, which may improve latency. And this is also something that Connor added support for. Now, one of the things that's one of the first bigger features that I worked on myself is full support for predicate registers. So before A600, if I'm not mistaken, Adreno only had a single predicate register, and we weren't doing any register allocation, and it was just handled kind of specifically in the scheduler. Then from A600, there were 3 more predicate registers that could be used in hardware, which meant we needed to do proper register allocation. Unfortunately, since they are so limited in how they can be used, these predicate registers, our existing register allocator couldn't handle them. So we had to add a new one, and a second register allocator. A very simple one, but still it's a register allocator, so it's kind of complex. Related to that, we added support for predication. So what we can do is for leaf branches, we can replace the branches by predicate instructions that kind of directly manipulate the execution mask. This has the advantage of using less hardware state. I'm not going to talk too much about it, but there's some state shared among waves related to branching that we don't have to set up in this way. We improved support for subgroup operations. So Adreno supports subgroup operations since the A600 series, but initially only in a very limited form. So more advanced instructions were added that we added support for. Also some more advanced operations at the API level, like clustered subgroup operations. Added support for 64-bit integers, which is mainly NUR lowering, but we had to do some custom lowering for, I think, also subgroup operations in ir3. We have support for repeated instructions, which I will talk a bit about in the next slide. Then, in terms of the newest generation A700 features, some of my colleagues at Igalia added support for 64-bit atomics and 8-bit storage and integers. Connor added support for ray tracing, which he just mentioned is actually ray query, not ray tracing, but I don't know the difference. There is, one of the things that I added support for was support for alias texture sources and alias render targets. And that's also one of the features I want to explore a bit further in the next slide. But let's first go to repeated instructions. So as I mentioned, Adreno is a scalar ISA, which means we can do vector operations. But they have this kind of interesting feature to simulate this in hardware. So what you can do is set a repetition flag on instructions. And what will happen is that this instruction is then executed n more times, and the destination register is incremented on every repetition. And you can set this R flag on sources, which causes the source to be incremented as well. And these two things together allow you to kind of simulate a vector instruction. It's really simulation though, because it kind of gets expanded to just scalar instructions, and there is no benefit in terms of runtime. It will execute in the same amount of cycles as, in this case, 4 scalar instructions would do. But that means it's kind of a way to compress code. So if code can be vectorized, the total code size will become smaller because of it. So how do we implement this? Well, first off, we realized that we kind of want to make sure that this doesn't interfere with any existing scalar optimizations. Because it doesn't have an actual runtime benefit, we would prefer to keep the other optimizations where possible. And the way that we do this is that we do everything in NUR as we were doing before in a scalarized version. All the way at the end, we vectorize it, and that's the way that we ingest it into ir3. But then once you do instruction selection in ir3, we select it again as scalar instructions. And the only thing we do is kind of adding them together in a repeat group, so that you can later easily recognize them. Then all the internal optimizations, including scheduling, they completely ignore these repeat groups. And only right before register allocation, we can kind of give a hint to the register allocator to ask it to try and allocate these registers consecutively, because that's what we need to be able to have them repeated. And the register allocator will try to do this, but if it fails, it will not do anything special to force it to be consecutive. And then after the register allocator, if it worked out and we have consecutive registers, we will compress these instructions into repeated instructions. Then I think I don't have too much time left, so I will quickly go over the one A700 feature that I found kind of interesting. It's about the sources of texture instructions, and I think Faith already briefly mentioned this, that we can have a lot of texture sources going into a sample instruction. And since we cannot all encode them directly in the instruction, the way that this works on Adreno is that you encode the first register of a consecutive range of registers into an instruction, but then you have to make sure that all the rest can actually be allocated into a consecutive range of instructions. This puts some strain on the register allocator. It might increase register pressure. It might also have to shuffle around registers to make sure they actually can be allocated in a consecutive range. And the thing that Qualcomm added in the A700 series to kind of make the situation slightly better is something called register aliases. So what this does is, instead of actually having to allocate values into a consecutive GPR space, we can allocate them any way we want, and then before executing the sample instruction, build an alias table that maps virtual GPRs into real GPRs, or even into immediate values or values in constant registers. And then presumably this table is somehow sent to the texture processor, which then uses it to remap registers before accessing actual values. So this means that we don't have to allocate a lot of consecutive registers. We also don't have to allocate registers for immediate values or constant registers, which we did have to do before. So this has a lot of advantages for coming out of register allocation. And I wanted to go over some the tooling that we use, but I don't have time left, so I propose that I stop here and take some questions. And then if people want to know about the tooling that we use, we can talk about it during a break. Thank you.
Hi, I have a noob question. In compiler language, what is a scheduler? What is it doing?
The scheduler is the optimization pass responsible for finding a good order of instructions. And that might have an influence on, for example, register pressure, so reducing the life range of certain values, or on the latency of instructions. So when an instruction needs, for example, 3 cycles before its value becomes valid, the scheduler might try to schedule useful instructions in those 3 delay slots. Because if you cannot do that, it has to insert NOP instructions, which are useless and will just waste cycles and space. So those are kind of the 2 main things that the scheduler is doing.
All right, I think, hello? Yep. I think we're at time. Thanks a lot for the presentation.
Yep.